In this lecture, I want to talk about the fundamental theorem of calculus for the second part. So, as I said, for the first part, fundamental theorem, anytime you see the word fundamental in the title, in the name of a theorem, pay attention. It's important. This theorem connects two branches of calculus, differential calculus and integral calculus, or instantaneous rate of change and area under a curve, or the tangent line problem with the area under the curve problem. So we've already talked about part one in another lecture, so now we're going to talk about part two, and I want to begin by defining this function. I'm going to call it a of x, and it's the integral, or the definite integral, from 0 to x of this function 2t dt. So I have, this is 2t right here. So it's just a linear function with a slope of 2. And let's think about what this means. All right. So it's the area from 0 to x. So we'd like to think about why this is a function of x. All right. So one way to think of it is, if I make x here, then the area, this area here, is the value, whatever x is. You know. So let's say that's 1. Then I would have a triangle with a base of 1 and a height of 2. 1/2 of that would be, a of 2 would be 1. So I could put x out here, all right, and then all of this would be a of x. Or I could go out further. I could come out here, and it's called this x, and then all of this. So the point here is that it's a function of x because depending on where x is, the function depends on where we put our x, right? So this could be 0 to 1, 0 to 2, 0 to 10, 0 to 1,000,000. The accumulated area, so you know, you can think of this as A standing for area or accumulated area, all right? So that's the way in which A depends on x, and we have this definite integral that actually defines a function of x. So now I want to go further with this and look at what happens if we evaluate this. So let's use the first part of the fundamental theorem of calculus, which says that I can evaluate this, I can find this area by finding the antiderivative and evaluating it at the endpoint. So the antiderivative of 2t is t squared, and we evaluate that at 0 and at x. So I end up with x squared minus 0 squared, which is x squared. All right. So in this case, I can find the area underneath this curve for any value of x by simply using x squared. If x is 1, then I know that the area is 1. If x is 2, then I know the area would be 4. If x is 10, then the area would be 100. All right. What about if I did, let's say I started it at -2 instead, and I went from -2 to x. So now I'm coming back this way, and I'm getting some of this signed area. This would be kind of a negative area because the heights of my rectangles would be negative in this case. But let's just look at what happens if we apply the first part of the fundamental theorem of calculus here. Well, I get the exact same thing as I do here, except I'm now going, instead of from 0 to x, from -2 to x. So I end up with x squared, whoops, getting ahead of myself, x squared minus 4, right? Because -2 squared is 4. All right, so now if I start back here at, say, -2, this minus 4 comes from, I have kind of a negative area underneath the curve here. So this part's all x squared minus this 4 here. Okay, what if I were to redefine this to be from 5 to x of 2t dt? Well, then I would end up with t squared from 5 to x, so that would give me x squared minus 25. So it would be minus 25 because if this were 5, then all of this area wouldn't be included because we'd be starting at 5 and just taking the area going to the right. All right? So why am I changing this lower limit? Well, I want to make the point that, I guess I could have done each of these in a different color. I can do it in a different color now. That for this a of x, note that a prime of x, so here is my a of x, it's x squared, a prime is just 2x, right? And for this a of x, a prime of x, is also 2x. If I take the derivative here, I get 2x, and the derivative of the constant is 0. And then finally, if I take the derivative of this a of x, a prime of x is still 2x. Take the derivative of that, that's 2x, that's 0. All right, so the point of this is it doesn't matter what the lower limit is, right? If I go from some number up to x, and then I take the derivative, notice that what I get back is basically the same function, except I've had a change of variable, right? This is now a function of x, where this was a function of t. All right, that idea is basically the fundamental theorem of calculus, the second part. So let me go ahead, go to the next page, and define that. See if I can get to this page too. But there's a page there. So if we define big F as the integral from a to x, right? So our lower limit doesn't matter, and we'd have f of t dt. And we've already seen how this big F depends on x. Then the derivative of this is just this little f, all right? Another way to think of it is if I take the derivative with respect to x of this function, then I just get back, I basically get back the same function, all right? So I'm taking the derivative of the integral, and it just gives me back the integrand, all right? So what this shows is that differentiation and integration are inverse processes, just like addition and subtraction undo each other, just like multiplication and division undo each other. Differentiation, if you take the derivative of the integral, you get back the original function. Likewise, if I were to take the integral of, I guess, sorry, this has to be a t, all right? Notice, though, that really all I'm doing is I'm making a substitution. I'm replacing f of t with its derivative, but this is going to give me back f of x, right? If I take, in other words, if I take the integral of the derivative, then I get back the function. Just like if I take the derivative of the integral, I get back the function. Okay, so let's just see how we might use this. Here's just a quick example to start us off. I take the derivative from 0 to x of the square root of t squared plus 1 dt. All right. Now, what's nice about this is I don't have to try to find the antiderivative of this function. Using the second part of the fundamental theorem of calculus, I know that if I take the derivative of the integral, I'm going to get back the function, but I'm going to, because my upper limit here is x, I'm going to change variables. This is going to be a function of x. All right. Let's look at a more interesting example. So here is one example. Example 1, we'll call it. Let's take a look at example 2. So in this case, I'm taking the derivative with respect to x of the definite integral from pi over 2 to x cubed of cosine t dt. All right. So there's more than one way to solve this, but let's first use the fundamental theorem of calculus. So one way to do this is let's do this substitution, let u equal x cubed. All right. So now I have f of u equals the integral from pi over 2 to u of cosine t dt. All right. And so I don't want equals here. So df du is just going to be cosine u. Now, what we're going to need here, since we're doing the substitution, we're basically doing a function, we're doing composition of functions, right? What we're going to need is the chain rule. So what I'm going to have is df du times du dx. Well, this is df du, and du dx is 3x squared. So this is going to be cosine u times 3x squared. We want everything to be, ultimately, we're taking the derivative with respect to x, so we need to get this back in terms of x. So I end up with cosine of x cubed times 3x squared. All right, so that's using the second part of the fundamental theorem of calculus to get df du. All right, and then using the chain rule. So we have to add this factor of 3x squared, the derivative of the inside function. So another way to do it is we can do it without the second part of the fundamental theorem of calculus, but we have to go through all the work that the second part of the fundamental theorem of calculus does for us. So let's just go through this. Again, the idea here is just to kind of give you some insight into what the second fundamental theorem of calculus, or the second part of it, means. So if I were to take the integral from pi over 2 to x cubed of cosine t dt, well, I know that the antiderivative of cosine, so basically I'm using the first part of the fundamental theorem of calculus instead of the second, because I know the antiderivative of cosine is sine. And I'm going to go from pi over 2 to x cubed. So using the first part of the fundamental theorem of calculus, I end up with sine of x cubed minus sine of pi over 2, which is sine of x cubed minus 1. All right. Now what we wanted originally was the derivative of this. So I have found another expression for this right here. So now what I want is the derivative with respect to x of sine of x cubed minus 1. All right? So I have to use the chain rule for this part, and the derivative of 1 is 0. So I end up with cosine of x cubed. That's the derivative of the outside function evaluated at the inside function times the derivative of the inside function, which is 3x squared. So we get the same thing back. It's just that we had to go through this work of finding the antiderivative. I mean, in this case, it was quite simple. Where the second part of the fundamental theorem of calculus is really helpful is if we end up with something here where finding the antiderivative would be difficult, or sometimes impossible, then the second fundamental theorem of calculus allows us to take the derivative of an integral and just get back the integrand without actually having to find the antiderivative. So this is, again, just kind of showing the connection between what we did with the first part of the fundamental theorem of calculus and the second part. Okay, so the last part, well, I guess there's just continuing. This is the last part, is called the Net Change Theorem. All right, and it says if I take the integral from a to b of f prime, big F prime, then it's just f of b minus f of a. And we've actually already seen this. If we go back, here's our notes from the first fundamental theorem of calculus. We had this relationship, right? So in other words, this was, if we just kind of look at this, what we found here, this was velocity, which was the derivative of the distance function, right? So what we ultimately did here, because we wanted to find the net change, in other words, I want to find the amount of distance that had been covered from 0 to 6 hours. So I had taken from 0 to 6, so that's what I have here, of s prime of t dt, or 0 to 6 of 30 minus 5t. That's the velocity function, which is the derivative of our position function. Okay, so, and then what we did here is we just found the antiderivative and we evaluated the endpoints. So that's what the net change theorem says. We take this derivative, we get back s of t, which is 30t minus 5 halves t squared. That's the antiderivative of this function right here. And we evaluated it at 0 and 6. All right, so if we do that, we get 30 times 6 minus 5/2 times 6 squared minus, when we plug in 0 here, that whole thing becomes 0. And if you recall, if you watched that first part of the Fundamental Theorem of Calculus lecture, you know that we got 90 miles. So this was our net change. And this is just, I wanted to come back to that example because that's an example, that's a precise example of the net change theorem, is this relationship between velocity, which is the derivative of our distance or our position function. And so we just go back to our position function and evaluate it at the endpoints. All right, that's kind of the net change theorem in action. So I just want to do one more example. I want to talk about the difference between displacement. So if we continue along this idea of velocity being the derivative of our position function, or the position being the antiderivative of velocity, we can think about displacement or about total distance. All right, and I want to talk about the difference between these two. So I'm going to use just a graphical example. So if I have a function like this, so let's call this A1, we'll call this A2, and we'll call this area here A3. All right, so displacement is just, so let's say we have a velocity function, then the displacement is just going to be the integral from A to B of our velocity function. And what that's going to give us is that first area minus the second area, because it's underneath the x-axis. This is a negative area, so to speak. And then plus A3. So if you think about these as signed areas, so the displacement just says, so another way to think of this is, you know, let's say you start at home, you go over to your friend's house, and then you go over to a restaurant just around the corner from your house. Displacement just says, it's just kind of looking at the distance you are by being at that restaurant, how far you are from your house. All right? That's ultimately what it'll give you. It won't, whereas the total distance looks at, if you know, the distance that you drove from your house to your friend's house and then back to a restaurant closer to your house, it gives the total distance. So in this case, it would be the definite integral of the absolute value of velocity. Whoops, there should have been a dt in there, and there's a dt here. And so the total distance just adds all of these up. It doesn't, in other words, because it's taking the absolute value, it considers all of these. It kind of flips it over, so to speak. So we're taking positive, positive, and positive, and just adding them all up. All right. So let's just do one example of a problem that asks for both displacement and distance. So let's say our velocity function is 5t minus 7, and we're looking for time between 0 and 3. So displacement is actually pretty straightforward, because you simply take the integral from 0 to 3 of 5t minus 7. All right, well, that's going to give me 5/2 t squared minus 7t. I'm going from 0 to 3. So that's going to be, what, 45 over 2 minus 21 for that part. And then minus, when I put in 0, I'm just going to get 0. Well, that's about 22. Well, not about. It's exactly 22.5 minus 21. So the total displacement is 1.5. Total distance, we have to work at a little bit harder, because what we have to know, so let's just take a look at this velocity function. So clearly at 0 we're at -7, so we're way down here. Where does it cross the x-axis? Well, that's going to be when 5t minus 7 equals 0. So if we bring the 7 over and divide by 5, it's 7/5. So if we're going out to 3, here's 1, here's 2, probably a little bit closer to 1, so we're going to have a function that looks something like this. All right? So this part's going to be negative, and if we're looking at the area, this area, A1 will be negative, and A2 will be positive. And so you can see that when we just go straight across from 0 to 3, what we're left with, this is 1.5, this area is 1.5 bigger than this one. That's what this displacement tells us. What we'd like to do is break this up into 2 and take this area and add it to this area. So what we're going to do then is we'll take the integral from 0 to 7/5, and we want to flip this over up this way, all right? So we take the negative of this function right here, negative of 5t minus 7 dt. That will give us a 1. Let's go ahead and, well, I'll go ahead and just set up the next one. And the other one is going to be from 7/5 up to 3. And there we're going to use the function because 5t minus 7 is positive from 7/5 up to 3. All right. So here I can just rewrite that as the integral from 0 to 7/5. The negative is just going to switch this around, 7 minus 5t dt. All right, and without going through all the gory details of this computation, I'm just going to tell you that will give you 4.9. All right, well, I guess I can just do one more step here. Let's say this is going to be 7t minus 5/2 t squared from 0 to 7/5. And if you do that computation, you get 4.9. Here, we're going to actually get the same thing that we got here, 5/2 t squared minus 7t from 7/5 up to 3. And again, without going through all the computations, I can tell you that that equals 6.4. All right? And this makes sense. The 6.4 is this part. This is 4.9. So if this were negative and you subtracted the 4.9 from the 6.4, you would get exactly the 1.5. But for total distance, instead of subtracting them, we want to add them. So it's going to be 6.4 plus 4.9, which should give us 11.3. All right, so this is kind of an example of the net change theorem. Total distance gives us the net change, where displacement, well, there are different ways of thinking about net change. This gives us kind of the net difference in our position, where this gives us the total amount of distance traveled. All right, so that is the second part of the Fundamental Theorem of Calculus.